Okay, I've already gone over most of what you need to know for radical functions. A radical function is a type of power function where the exponents represent the most basic of radical functions. A radical function can be written, and we looked at this in a previous video, the nth root of x to the p. So we're looking at being able to flow fairly efficiently between this form and this form, where the bottom number always tells you the index, or what is the root that we're going to take, and p is the power that we can raise the inside the radicand to the power of p. So I already talked about this, so there's really not a lot to discuss here. Just keep in mind the one rule of thumb here is if this is an even root, you only have it in the first quadrant. If it's an odd root, you have things in both the third and the first quadrant. You have this symmetry about the origin on our odd roots. And you can take the odd root of negative numbers, so that's not a problem. We're not going to limit our domain there. And they give you that information in those boxes. What we're going to do is just quickly look at a couple of graphs here. We have to graph and analyze each function, describe its domain, range, intercepts, and end behavior, continuity, and where the function is increasing or decreasing. Just a little twist on this, nothing real major here. But what I did is I created a graph for you of the equation for f of x. If we look at describing its domain, whenever we talk about domain, we're searching on the x-axis. Are there any breaks or gaps within that problem? So if we look at this, it's a nice smooth continuous curve, so our domain is going to be a set of all real numbers. We can designate that over the interval from negative infinity to infinity. The range has a little bit more that we have to deal with. We can see they're both going towards negative infinity, so we know it's going to negative infinity, but it's going to hit a maximum value right up here. So what we're going to do is we're going to use our graphing calculator to find that maximum.
Morning, this is Mr. Adams with your announcements. A few more quizzes.
Pause for announcements.
Picture retakes will be on November 1st.
Okay, announcements are over. So what we're going to do is we're going to use our calculator to find the maximum point for this. So I already have loaded in the calculator the equation negative 12. There it is. I just had to find it. That's the equation I'm going to graph. Here's our graph of that function. Just go to your second, calculate a maximum, and find that maximum value. So we're just going to use our calculator to find that. We could also put in 0 for x, and that would help us get it as well. So anyway, put in the right bound, left bound, and that's going to help us find the maximum value. Okay, don't worry if you get in a statement like this, 1.1626 e to the negative 6, that means it's 0. When x is a 0, our y value is approximately 1.71, so we'll round it to the hundredths place, so it's approximately 1.71. And then that's going to be inclusive, so put a square bracket on that. So we got our range. The intercepts. The y-intercept we just found because that was the ordered pair 0, so that we can just record. The y-intercept is 0, 1.71. As far as the x-intercepts, the nice thing about this graph, it does have symmetry about the y-axis, so if we find one, we know what the other one will be. So again, we'll use our friend the Wabbit calculator, and we can go ahead and find our intersections of the x-intercept. So we'll go to second, calculate. This is called the 0 of the function. These are the inputs that create an output of 0. That's why they have the name 0 of a function. Just got to be on the left bound side. Hit enter. You've got to go to the right bound side. Hit enter, and it's going to search in between that range or interval, and it tells us that we have a 0 at negative, or at a positive 0.65. So round to the nearest hundredth is 0.65, comma 0. We're going to use the symmetry of the graph, so that means our other x-intercept is negative 0.65, comma 0, and I'm guaranteed it to be symmetrical to the y-axis because I can replace x with a negative x and get the same expression, because when we square a negative, it's going to become positive. So we can use that test for symmetry if we have any doubt about it at all. Next thing we're going to do is look at the end behavior. The end behavior on this graph, clearing out some workspace. As x approaches a negative infinity, y approaches a negative infinity, and as x approaches a positive infinity, y approaches a negative infinity. So we could say this in another way. We could say x approaches either a positive or negative infinity, y approaches a negative infinity. So if we have our end behavior taken care of, continuity, this graph is continuous over its entire domain. So when we do our continuity, It's continuous over the interval from a negative infinity to a positive infinity. Finally, where is the function increasing or decreasing? Again, read your graph from left to right whenever you're answering the question about increase or decreasing. Our graph is increasing all the way up here until we hit our maximum point. So it's increasing on the interval from negative infinity up to, but not including, our maximum point, which I believe was 1.71. Put a parenthesis on that because we don't really need to include that point. That's the transition point. It's not increasing there. That's where it has a rate of change of 0. But on the other side of that, that's where our graph is decreasing. So on the interval from 1.71 to positive infinity, we have an increasing or decreasing graph. So that's all we need to discuss about that problem. Let's move on to 5b. The one thing to watch out for, I put it up here as well so that you can pay attention to it. Keep in mind when you have an even root of a radical, all you have are the positive values, so it's going to be restricted to this first quadrant. So that's our entire graph. Describe the domain. Our domain is definitely restricted. You can see by the graph that we can't put in any value that is less than or equal to less than 2. So our domain is going to be from 2, and because it includes 2, it's 2 to positive infinity. And if you don't trust that just from the graph, you can always plug in the 2 there and make sure that 2 times, putting the 2 for x, 2 cubed minus 16. We just have to make sure this comes out to be greater than or equal to 0. So that should be 2 times 2 cubed is 8, and that minus 16, and we got 16 minus 16. Is that greater than or equal to 0? Yep, it's equal to 0, so therefore we have the right number. So, like I said, if you don't trust what you're seeing on the graph, you can always plug in what we know about this having to be greater than or equal to 0. So our domain is this. Our range, just as we've seen in all these even root ones, our ranges go from positive infinity, say that correctly here, it goes from 0 to positive infinity. So including 0 up to positive infinity. Our intercepts, it does not have a y-intercept, so there's no y-intercept, but the x-intercept is at the ordered pair to 0. As far as continuity, end behavior is next. Our end behavior. So the only end behavior that we have to talk about is as x approaches a positive infinity, then y approaches positive infinity as well. There's really no end behavior that we can talk about on this graph because it has a definite ending spot at 2, 0. So x doesn't go to negative infinity, it has a restricted domain. And continuity, it is continuous over the entire interval from, and again using the correct bracket because we can go from 2 to infinity. And we have to do increasing or decreasing, and this is pretty easy to see as we go from left to right for the x's. This is continuously increasing throughout the entire graph. So it's increasing on the same interval from 2 to infinity. So just a couple more graphs to interpret on those. Finally, in our discussion, we want to be able to solve radical equations. The directions are giving you some great ideas on how to do this. Whenever you have a radical in your equation, you first want to do everything you can to isolate that radical. That means you want to get it on one side of the equation by itself. Once you have that radical isolated, you want to raise it to the appropriate power. So we're going to see some square roots, some cube roots, maybe even some fourth roots, which means we're going to have to raise each side to a power of 2, 3, or 4, whatever the equation tells us to do. So starting off with some examples here, and you can read through the rest of that on your own. But in 6a, here's our equation. It's obvious to see that we have a radical in our equation. So our basic scheme on these is always to isolate the radical. So really I want to get this square root of 18x minus 18 isolated on the side by itself. So we're going to move the 3 over. So we'll have 3x minus 3 equals the square root of 18x minus 18. Okay, so because this is a square root that you don't see an index, it's automatically a 2. We want to undo that square rooting by squaring. So be really careful when you do these. What we got to do is treat both sides equally. The golden rule of the equation says whatever you do to one side, you must do to the other. Well, I'm going to square this side, which means I have to square the left side. When you square the left side, we're squaring a binomial. And when you square a binomial, you always get a trinomial. So in the back of our minds, we're taking 3x minus 3 times another 3x minus 3. The short way of doing this is you square the first thing, which is 9x squared. You double the two things that are in the inside, so you got a negative 9x, and you double it is a negative 18x. And then we want to square the last thing, so negative 18x, square the last thing, which is negative 3 squared is plus 9. Now that equals, now on the other side, we want to make sure that we square the square root. So when we square a square root, it will undo it. So 18x minus 18. Now when we look at our equation, we've got a quadratic equation, and now we have to go through how do we solve quadratic equations. It's telling us quadratic because of the square. So that means we want to get one side equal to 0, and then either factor quadratic formula. So I want to move the 18x over here. To do that, I'm going to have to subtract 18, so it's going to be 9x squared minus 36x. I also want to move the negative 18 over here to the left, so that means I'm going to have to add 18. So that's going to give us a plus 27 equals 0. One of the things I noticed about this equation right away is every one of these numbers is divisible by 9, so we can help improve our position by either factoring out a 9, or in this case I can divide through the whole equation by 9. I'm going to just factor it out here, so I'm going to take out a 9. We'll have x squared minus 4x, then plus 3 equals 0. And now we have some decisions to make. See if we can find any ways that we could factor this. Are there any factors of 3 that add up to a negative 4? And in my mind, I'm thinking of a couple of factors right away. The only factors of 3 are 3 and 1. The signs have to be the same. They both have to be negative. So minus 1 minus 3 equals 0. Okay, now we're going to apply our zero factor theorem at this point, which means if we've got, try that again, zero factor theorem, which means if we've got 1, 2, 3 numbers that are multiplied together and our answer is 0, one of these 3 numbers has to be 0, and I know it's not 9. So what can I put in for x to make this equal to 0? And our answer is 1. And what can we put in for this x to guarantee an answer of 0? And that answer is 3. So it appears that we have 2 answers to this radical equation, 1 and 3. Final thing that they have in their review on these radical equations, you have to really make sure that you check these answers. You have to be really disciplined at doing that, because if you don't, what you could do is you could have an extraneous solution. So here's the big word, extraneous. If you have an extraneous solution, it just means you have an extra solution, and sometimes these extra solutions are created when you come back up here and you square. Because when you square, you don't know if this number over here was a positive or a negative. When you squared it, it would come out to be positive. So every once in a while we get some extras that cling onto this, and we got to sort them out. So what are we saying we have to do? Basically, we have to take our original equation, 3x equals 3 plus square root of 18x minus 18, and we got to plug in our solutions to make sure they work. So I'm going to plug in this 1. This is 3 times 1 equals 3 plus the square root of 18 times 1 minus 18. And this is a 3 equals 3 plus the square root of, well, 18 minus 18, which is 0, and the square root of 0 is 0, so 3 equals 3. I've just confirmed that 1 is a solution to this inequality, or this radical equation. But I should also check 3 and make sure 3 works. So now I'm going to do the same process, only replacing x with 3. 3 plus square root of, now I got 18 times 3 minus 18. This is 9 equals 3 plus the square root of 18 times 3, 24, carry the 1. Looks like carry the 2, 54 minus 18. That's 9 equals 3 plus. Now I got to take 54 minus 18, so 54 minus 20 would be 34. Come back up 2 is 36. Take the square root of 36. That is 6, and 6 plus 3 is 9. So 9 equals 9, you bet. So both of these checked out this time. That does not always happen. So be very disciplined, check your solutions, and make sure that they're going to work each and every time. Okay, clearing the board. Okay, so cleared the board, and now we're going to work on 6B. 6b, again, your general principle, don't lose track of what that says, is you want to make sure that you want to isolate the radical first. So the first thing I want to do is I want to get this positive 3 over to the right side so I can isolate the cube root of 4x plus 8, which equals, now if I move it over, I have to subtract 3, so 7 minus 3 is 4. Now, we got to get rid of our radical, the cube root. To undo cube rooting, you raise it to the third power. So raise both sides to the third power. The cubing will undo the cube rooting, so we'll have 4x plus 8, and it's going to equal a 4 cubed. That's 16 times 4, which is 64. And then we have to subtract 8. So 4x equals 64 minus 8. That should be 56. And then divide both sides by 4. And 56 divided by 4. 56 divided by 4 is 14. So we believe our solution is 14. Again, staying really disciplined with these. It's probably more important with the even roots than the odd roots, but it's still good practice to plug these back in and make sure they're going to be fine. So we go to the cube root of 4 times 14 plus 8. We add 3, and we want to check to make sure we get 7. So we have the cube root of 14 times 4 is 56 plus an 8. Then you have to add 3 to make sure we get 7. And 56 plus 8, and that was our cube root of 64 plus 3, is that equal to 7? And then the cube root of 64, the cube root of 64 is 4. It's 4 times 4 times 4 is 64, plus 3 equals 7. That checks, so we want to keep the solution. So our solution set, although I didn't write it as a set last time, is 14. And you can always put it in face brackets to represent the set of solutions. Okay, cleared the board off, and now we have our final example on how to solve radical equations. This one by far is a more complicated one. If we try to do our first step, remember our first step, the first idea is to isolate the radical. No matter what we do to this problem, we're always going to be managing and dealing with this 3. So if I move it over, then I haven't isolated the radical on the left. So there's no way to completely isolate the radical, so this is going to be more of a double or two-step squaring process to get this done. So there's no advantage to moving the 3 over, so what I'm going to do first is I'm going to say, okay, I need to get rid of this radical of square rooting, so I'm going to square. Now that means I got to square this whole side on the right. To save a little space over here, I'm going to work space over here. So if I square a square root, we'll just end up with x plus 7, which achieved one of our goals, and that was to eliminate a radical. But now we've got this 3, I'm going to be a little bit more careful with this. 3 plus the square root of 2 minus x, and we have to raise that to the second power. Keep in mind, whenever you take and square a binomial, you're going to create a trinomial. So you have x plus 7 equals, we have to square the 3, which is 9. We have to double the outside inside, so we're going to double that. Right now we have 3 times the square root of 2 minus x, so we double it. It's going to be plus 6 times the square root of 2 minus x. Then we have to square the last term, so if we square the last term, now we're squaring a square root, which will undo it, and we'll end up with plus 2 minus x. So we didn't completely get rid of our radicals. We still have one radical left, but we have improved our position. We went down from one radical down to, or from 2 radicals down to 1. We're going to clean this up. We'll collect all the like terms that we can. The 9 and the 2 are like terms, give us an 11. Plus 6 times the square root of 2 minus x is minus x. Now we're down to just one radical left in our equation, so now we can try to isolate that radical, and that's going to be our strategy. I want to move the x, negative x over here with its like term, so to undo subtracting, I add it, so it'll give us 2x. I want to get rid of the 11 that's sitting over here. To get rid of the 11, we're going to have to subtract it, so it's going to be 7 minus 11, or minus 4, equals 6 times the square root of 2 minus x. Okay? And I would say this is the only exception when you say isolate the radical. If you have a number multiplied times a radical, if you leave it there, it's not really that difficult to square it. I'm going to just leave this 6 here. Said this is the exception. If I got multiplication or even division, I can leave it there and go ahead and square. I don't have to isolate it completely with the product. So square both sides to try to eliminate the radical. So I'm going to square both sides. And we're squaring a binomial. It's going to be a trinomial, so we're going to square the first thing, 4x squared. We're going to double the outside inside. That's a negative 8x. We've got to double it, so minus 16x. Then we have to square the last term, so negative 4 squared is plus 16 equals. Now this is where we got to make sure we square this correctly. So it's 6 times the square root of 2 minus x. We got to have another one of these, which is 6 times the square root of 2 minus x. And if I rearrange this, it's really a 6 times 6 and a square root of 2 minus x times the square root of 2 minus x. Well, this is a 6 squared and the square root of 2 minus x squared. Or what we're doing is we're using our properties of exponents. We can use our power property of exponents. It's 6 squared, which is 36. And if you square a square root, they undo each other. So we're going to be left with 2 minus x. Okay, we're still continuing. We've cleared all of our radicals, so our position is greatly improved. What I want to do is distribute the 36 at this point. And I've got 36 times 2, which is 72. And then 36 times a negative x is a negative 36x equals a 4x squared minus 16x plus 16. All right, it's again coming down to solving a quadratic equation. So we want to get everything on one side, get one side equal to 0, so 4x squared. You want to add your 36x, so 36x minus 16 is going to be 20x. You want to undo subtracting 70, or adding 72, so you want to subtract. So it's going to be a negative. And then we got to take 72 minus 16. So 12 minus 6 is 6, and had to borrow, so this is 56 equals 0. All of these numbers are divisible by 4. If I look at this, they have a monomial factor that we can take care of. I'm going to factor out a 4, and it's x squared plus 5x, then minus, and 14 goes into 56 14 times, equals 0. We're getting closer. Then you just have to evaluate. Do you think you can factor this? If you don't think you can factor it, use your quadratic formula. So it's 4 times. I believe I can factor that trinomial. The factors of 14 that are 5 apart are 7 and 2, so I want to go x plus 7, x minus 2. That gives me the correct factorization. Now we're going to apply the zero factor theorem, which says one of these 3 numbers has to be 0, and I know it's not the 4. So what do I put in for x to create a factor of 0? And that is x could be a negative 7, and the other one, x could be equal to a 2. Now these are our plausible or possible solutions. They're never final until we check those back into our original. So we're going to go all the way back up here, and we're going to test those into our original equation. So we got to test the order, or the solutions of negative 7 and 2. So negative 7 and 2 are the solutions we're testing. Do both of these survive? So we're going to take the square root out. I'm going to put in a negative 7 first, negative 7 plus 7. Does that equal 3 plus the square root of 2 minus, and then it's going to be minus a negative 7. So negative 7 plus 7 is 0, square root of 0 is 0, so this side is equal to 0. And over here we have 3 plus, and then we've got 2 minus a negative 7, which is really 2 plus 7, or 9, and the square root of 9 is 3. So that means we've got 3 plus 3, and 3 plus 3 is 6, and 0 is not equal to a 6. So what does that tell us? It tells us that we're going to have to eliminate negative 7 as a solution. Can't be used. Okay, so going back, and we got to do one more final check. We got to see if 2 is an appropriate solution. So we're going to take the square root of 2 plus 7. Does it equal 3 plus the square root of 2 minus 2? So 2 plus 7 is 9. Square root of 9 is 3. So we know we have a 3 on the left side. On the right side, it's 3 plus the square root of 0. Square root of 0 is 0, so 3 plus 3. Or 3 plus 0 is 3. It checks. So 2 is the only thing that survives, so our solution set is just going to be the value of 2. Okay, so I want to really stress the importance of checking your solutions because of those extraneous solutions that can be created whenever you square or take an even power to one of your equations that you're solving. Okay, so should have you up to speed on how to solve radical equations. That's going to be a main emphasis and thrust throughout this lesson now. So That should be all that we need to discuss. I'll get your assignment posted, and we should be able to get going on it in class.